Hi everyone, today a video in the bonding and structure topic looking at physical properties and bonding. Now this will probably be very familiar to you, but the first thing to talk about really is states of matter, physical states. And so we know that in a solid, the molecules are arranged in regular repeating patterns. They're held very, very firmly in place. They can vibrate, but they can't actually move. So it's rigid, fixed shape, a fixed volume. And so we have this very regular arrangement of particles. The evidence for this is that we have crystal shapes with very straight edges, and so solids have these definite shapes. We say that the spacing is fairly close. These particles are very close together, they're not far apart. And the evidence for that being that they're not easily compressed, so they must be close together already. We know that they can vibrate around a point. Diffusion is very slow and solids expand on heating because they have more energy and they vibrate more. We can then go to look at if we increase the energy so much that they then vibrate so much that they then actually break apart. This becomes our liquid. And so now the molecules that make up our liquid flow very easily around one another. They're kept from flying apart by attractive forces. This is our intermolecular forces between them. And liquids will assume the shape of the container you put it in. So this is not a rigid shape, it doesn't have a fixed shape, but it does have a fixed volume. And so we can say that we have a random arrangement of particles, and we know that liquids will change their shape to fill whatever container they're in. The spacing is still fairly close, because liquids aren't easily compressed, and the movement is what we say is rapid jostling. Diffusion is fairly slow, but we know that liquids evaporate. And then finally we can go to look at a gas. Here we have these molecules that can fly in all directions, often at high speeds, and they're very, very far apart, and that's because our attractive forces between them are really quite insignificant. So it's not a rigid shape, it doesn't have a fixed shape, and it doesn't have a fixed volume. And so our arrangement of particles is random again. Again, a gas will fill its container. The spacing is very far apart, and one of the ways that we can show this with evidence is that the gases are easily compressed. So unlike solids and liquids that aren't easily compressed, gases can be compressed easily. So they must be at least further apart than a solid and a liquid. I mean, the movement here is very, very rapid. And so diffusion is very, very rapid, and gases exert pressure. And so generally we can think about starting with a solid. We heat it, we have particles vibrating around a point. Eventually we reach the melting temperature, Tm. Here we then get a liquid, so the particles can now move, but they are too close to travel far except on the surface. And those particles that are on the surface, if we continue to heat it, are the particles that can escape. Essentially they are, imagine the particles that are in the bulk of the solution in the middle of it. To be able to escape, they'd have to move to the top of the surface and then escape, whereas the particles that are already on the top of this surface can escape more easily. And so again, we have this evaporation, we can heat it more and more, and eventually we'll reach our boiling point, Tb. And here we have our particles that are essentially free and have very rapid random motion. And so these are our physical changes, our sort of physical states of matter, solid, liquid, and gas. And the final one to talk about is something called plasma, which is at very, very, very high temperatures, atoms will start to lose their electrons. And so this mixture of electrons and nuclei that results is called plasma. But for the most part, we can think about our three states of matter being solid, liquid, and gas. So we've talked a lot about this on the previous slide, but when we heat a solid, energy is supplied to the solid particles. They vibrate more around their fixed positions. And so this very slightly increases the average distance between the particles. And we said that a solid expands as it's heated. Then we get our actual melting, so going from solid to liquid. It's also sometimes called fusion. Now even more energy must be supplied to turn this closely packed, ordered, vibrating particles into a state where they are able to move randomly, but still close together. Now the energy is required to weaken the forces that hold the particles together in the solid state. So obviously in the solid state, because they can't move, it's obvious that we have very, very strong forces that hold them together. In a liquid, we said that they're able to move, but they're still kind of held close by intermolecular forces. And so this will be called the latent heat of melting, or the enthalpy change of melting. Now, when a solid is melting, the temperature doesn't change because all of the heat energy that I provide is being absorbed to break the forces between the particles, to weaken those forces. So if I just have my solid, as I heat it, the temperature of that solid rises and rises until we reach the melting point, and then there'll be a period where the temperature actually doesn't change for a bit because the heat isn't going into changing the temperature. The heat that we're providing is going into breaking those intermolecular forces, breaking the forces between the particles. Now, enthalpy is just a heat change. It's actually a heat change that we measure at constant pressure. Now, heat is just an energy, form of energy, but temperature is what we define as the average kinetic energy of the particles. It relates to their speed, how fast they move. The greater the energy, the faster they move, and the higher the temperature. So temperature really is essentially the average kinetic energy, the average heat, if you like, of the particles. We can then heat a liquid. The particles in the liquid move more quickly, they have more kinetic energy, they move faster. On average, if they move faster, the particles move a little bit further apart and liquids expand on heating. We can then get our liquid to gas transition, boiling, also called vaporization. Here, we have to supply enough energy to break all of the intermolecular forces between the particles. And the particles in a gas are very far apart and they move independently. We have very, very weak, if any, intermolecular forces. And this is called the latent heat of vaporization, or the enthalpy change of vaporization. And as we had with melting, as we get to this point of vaporization, if we carry on heating through this vaporization, there's no change in temperature because all of that heat energy is going into breaking the intermolecular forces. And then finally, we can heat a gas. Again, like with the liquid, if we supply energy to these particles, they will gain kinetic energy, they move faster, and they get further apart. And gases expand a great deal when you heat them. So this then brings us on to look at some crystal structures. So crystals are solids. And when we talk about a crystal structure, what we really mean is we have particles that have a regular arrangement. And they're held together by forces of attraction. Now these could be actual strong bonds between atoms, covalent bonds, ionic bonds, metallic bonding, we've talked about those in a previous video, or they could be weaker intermolecular forces. So these are your van der Waals, dipole-dipole, or hydrogen bonds, and again we've talked about those in another video as well. Now the strength of the forces of attraction between the particles affects the physical properties of the crystal. As you can imagine, the stronger these intermolecular forces or actual the forces between our particles are, the higher the melting temperature. It takes more energy, you have to put more energy in to separate them, and therefore the greater the enthalpy of fusion. And so the key thing is the crystal has this regular arrangement of atoms. You can see that sodium chloride example to the right. We have this lattice structure of sodium chloride, and we have this generally kind of repeating sort of idea that we have this very, very regular three-dimensional structure extending out in the 3 dimensions and kind of infinitely going on. We've just shown a small part of it here. And there are 4 basic crystal types. Ionic crystals. Now we said that ionic compounds have very strong electrostatic attraction between oppositely charged ions. Now sodium chloride, typical example. And so ionic compounds, because we have very strong electrostatic attraction between actual ions, sodium cations and chloride anions in this case, ionic compounds have very high melting points because we have to put a lot of energy in to actually physically separate those ions. The second is metallic crystals. So metals exist as a lattice of positive ions in a sea of delocalized electrons. We have this regular arrangement of positive metal ions in this lattice structure, and then we have this sea of delocalized electrons. Remember that delocalized means their electrons are no longer associated to a particular atom, and they can essentially move freely around all of the ions here. And so this arrangement of ions extends infinitely throughout the crystal, like it does in ionic crystals. We have this infinitely repeating pattern in 3 dimensions. And again, we therefore have high melting temperatures because we have strong metallic bonding. Again, strong electrostatic attraction between the positive ions and the sea of delocalized electrons. The third is a molecular crystal. So these consist of molecules, small covalently bonded species that are held together in a regular array by intermolecular forces. So again, these are molecules that essentially are in a lattice. They're molecules that are a regular arrangement. And they're held together by intermolecular forces rather than actual covalent bonds. So the covalent bonds that are within the molecule hold the atoms together, but they do not act between molecules. It is the intermolecular forces that act between the molecules. And intermolecular forces are much weaker than actual covalent ionic or metallic bonds. And so molecular crystals have a much lower melting temperature and enthalpies of melting. Now, an example of this is iodine, molecular iodine, I2. Now, we have a very strong covalent bond between the two iodine atoms. This is an example of a 100% covalent bond because we have no difference in electronegativity. And since the iodine molecules have a large number of electrons, they have a big molecular mass, the van der Waals forces are strong enough to actually hold the molecules together, but the crystals are quite soft and they break easily. And so it has a low melting temperature and it sublimes very easily. Sublime means that it goes from a solid to a gas without going through a liquid phase. And they don't conduct electricity because there are no charged particles. So it's unlike a metal lattice or an ionic lattice where we have charged particles that if we allow them to move, they can conduct electricity. Here, in this molecular crystal like iodine, because we have no charged particles, they don't conduct electricity. But the key thing is that while we have strong covalent bonds between the actual atoms, it is much, much weaker intermolecular forces that act between the molecules. And that is what we break when we talk about melting and boiling a molecular crystal. So they have much lower melting and boiling points because it's much less energy to put in to break the weaker van der Waals force. And you can see at the bottom that there's actually that sort of crystal structure of the iodine molecule showing this regular arrangement of where these iodines go. And this is what we'd something call a unit cell, essentially one kind of sort of snapshot of the whole crystal structure. And then finally, macromolecular crystals. So covalent compounds are not always made up of small molecules like iodine. In some substances, the covalent bonds extend throughout the compound. Again, we have this idea of a kind of infinitely extending series of covalent bonds. And they have the typical property of a giant structure that's held together with strong bonds. So like the ionic crystals, we have this very giant structure of this kind of regular arrangement extending in 3D in these three dimensions. And so therefore we have very high melting points. The same here for macromolecular crystals. So these are covalent compounds, but they are not small molecules. We have this kind of infinitely extending array of covalent bonds. And so high melting points, and the two examples we'll look at are diamond and graphite. So first of all, look at diamond. So diamond is pure carbon, just carbon, C, with covalent bonds between every carbon atom and with these covalent bonds extending throughout the entire structure. And so each carbon atom forms 4 covalent bonds with other carbon atoms. So each of our carbon atoms are arranged in a tetrahedral fashion. Each carbon atom is still technically tetrahedral. Now each carbon atom is in an identical position in the structure. It's surrounded by 4 other carbon atoms. So each carbon is always bonded to 4 other carbons. And so the atoms form a 3-dimensional lattice, a giant 3-dimensional lattice of very strong covalent bonds, and this gives it the following properties. Because we have these exceptionally strong covalent bonds, we have a very hard material. Here we don't have intermolecular forces acting because it's not made of small molecules. Instead we have this extended array of actual covalent bonds, so when we melt and boil these things, we are actually breaking the covalent bonds. Now covalent bonds are strong, and so we have a very high melting point. Diamond's melting point actually is over 3,700 Kelvin. Room temperature is 298 Kelvin, so you can see the huge difference there. And diamond doesn't conduct electricity because there are no free charged particles. So the next one to look at is graphite. So graphite is also pure carbon, but the atoms are bonded and arranged differently from in diamond. So here there are now 2 sorts of bonding. There's strong covalent bonding and weaker van der Waals intermolecular forces. So each carbon atom forms 3 single covalent bonds to other carbon atoms. So remember in diamond we had each carbon atom forming 4 covalent bonds. Here we have each carbon atom forming 3 covalent bonds. And because it forms 3, every carbon atom is in a trigonal planar arrangement. Now, because it's only made 3 bonds, carbon, of course, has 4 electrons, and so every carbon atom is left having a spare electron in a p orbital that is being unused. And so this arrangement produces a 2-dimensional layer of linked hexagons of carbon atoms. And so you can see at these sort of pictures at the bottom, every carbon being in this trigonal planar arrangement ends up having these sort of interlinked hexagons, and it's 2-dimensional in one plane, essentially. Now, the p orbitals that have the spare electrons in are at right angles to this plane. So essentially, if the plane you're thinking of here is sort of horizontal, the p orbitals are actually vertical. And so what they do with these p orbitals with the spare electron, they actually merge above and below the plane of the layers. But what this means is that our electrons essentially then become delocalized. They're no longer stuck to just being on that p orbital, but they become delocalized and they can move anywhere within the layer. And this adds to the strength of the bonding. These delocalized electrons allow graphite to conduct electricity. And so graphite conducts along the planes, but not between them, not at right angles to them. Now, there's no covalent bonding between the layers of the carbon atoms. The layers, the 2D layers, are held together by van der Waals forces. That's these 2 types of bonding. So within the layer, what we call our intralayer, we have very strong covalent bonds. Between the layers, what we call our interlayer forces, we have just weaker van der Waals forces due to those delocalized electrons from the p orbitals. And so what that means is that while the layers are sort of quite weakly held together, they can actually slide over one another, and it makes graphite quite soft and quite flaky. So graphite is a soft material, diamond is hard, graphite is soft. It also has a very high melting temperature, and it actually breaks down before it melts because of this giant structure. And unlike diamond, it does conduct electricity along the planes of the hexagons because we have these delocalized electrons. And so what we call graphite and diamond are allotropes of carbon. And what we mean by that is that they have exactly the same, they're made from the same element, essentially they're both just pure carbon, but they have very different arrangements of those atoms. And so the diamond structure was our tetrahedral carbons, the graphite structure is our trigonal planar carbons in layers, with delocalized electrons and van der Waals forces holding those layers together. So, in summary, in covalent bonding, the electrons are shared between atoms. In ionic bonding, the electrons are transferred from metal atoms to non-metal atoms. That creates a cation and an anion, and then we have strong electrostatic attraction between them. In our covalent bonding, remember that it was the electrostatic attraction between electrons and nuclei, but there was technically no ions, they're just atoms. And in metallic bonding, we have our electrons spread across lots of metal atoms, this delocalized sea of electrons, in between our regular arrangement, our lattice of metal ions. And again, that's electrostatic attraction between our electrons and our metal ions. Now, you can usually tell the type of bonding in a compound if you know what type of atoms it contains. So if it only contains metal atoms, then it'll be metallic bonding. If it contains metal and non-metal atoms, it will likely be ionic. And if it contains non-metal atoms only, it will likely be covalent. We can then also think about the electrical conductivity. So we know that metals conduct electricity as solids and also in the liquid state. Because of the metallic bonding, we have the current being carried by the delocalized electrons. In ionic compounds, they conduct electricity, but not when they're solid, only when they are in the liquid state, when they are molten, or if they are dissolved in water. And the reason is because when they are solid, we have our ions that are in these fixed positions. They can't move, and we need to have movement of the ions to carry the charge and therefore conduct electricity. So ionic compounds only conduct in the liquid state or dissolved in water. And generally, on the whole, covalent structures don't conduct electricity because normally there are no charged particles in order to carry the current. Most covalent compounds are also insoluble in water, but some react to form ions. If they do happen to react to form ions, then they can conduct electricity. But generally, on the whole, covalent structures don't conduct electricity. We can then start to think about the summary of the structures we've covered. So in a simple molecular structure, this is composed of small molecules. These are small groups of atoms that are strongly held together by covalent bonds. So between the atoms in the molecules, very strong covalent bonds, but remember that the forces between the molecules, the intermolecular forces, are much, much weaker. And so examples of these are chlorine, Cl2, water, H2O, sulfuric acid, H2SO4, and ammonia, NH3. Very strong covalent bonds between the atoms, much weaker intermolecular forces between the molecules. So remember that these were either van der Waals, dipole-dipole, or hydrogen bonding intermolecular forces. In a macromolecular structure, we have a very large number of atoms that are linked in a regular three-dimensional arrangement by covalent bonds. So again, we have these strong covalent bonds, but now we don't have small molecules. We have these kind of extended array, this kind of infinitely extending array of covalent bonds. And so examples here are the diamond and the graphite that we've just covered, as well as silicon dioxide, silica, SiO2. And this has exactly the same structure as diamond, that sort of tetrahedral arrangement of silicon and oxygen atoms. We then have giant ionic structures. So this is our lattice of oppositely charged ions, our regular arrangement and our regular kind of repeating arrangement of oppositely charged ions. For example, calcium fluoride, CaF, or sodium chloride, NaCl. And then finally, we talk about metallic bonding, this regular lattice, again, this regular three-dimensional arrangement of positively charged metal ions held together by a cloud or a sea of delocalized electrons. This then brings us on to melting and boiling points. So simple molecular compounds have low melting and boiling points. Therefore, there must be covalent bonding present. Remember that when we melt and boil simple molecular compounds, we're not actually breaking the covalent bonds, we are separating the molecules. And so we're actually breaking the intermolecular forces, which are much weaker than the covalent bonds. So very low melting points and low boiling points is pointing you towards the fact that you're breaking weaker intermolecular forces rather than actual bonds, and therefore that it would be a simple molecular compound with covalent bonding. If we have one of the giant structures, for example ionic, macromolecular, or metallic, these tend to have much higher melting and boiling points. But of course the bonding here could be a number of things. It could be ionic if we have an ionic structure, metallic if we have a metallic structure, or covalent if we have a macromolecular structure. And remember, as we said on one of the first slides, that typically as we heat our species, whether it be a solid, a liquid, a gas, we have our temperature rising. But when we reach both the melting point and the boiling point, here the extra heat that we supply actually goes in not to raising the temperature of the species, but actually into breaking the intermolecular forces. And hence, for example, when we have the boiling point of liquid to gas, as we supply more heat, we actually have no temperature change for a bit because all of that energy is being supplied to break the intermolecular forces. And so, as I've just said, we're breaking these intermolecular forces between the molecules in simple molecular compounds, not the covalent bonds between the atoms themselves. And so it is the strength of the intermolecular force that determines the melting point and the boiling point. And we've talked in a previous video about the three types of intermolecular force. In increasing strength, they are van der Waals, dipole-dipole forces, and hydrogen bond. Remember that van der Waals forces was to do with the electrostatic attraction essentially between the positively charged nuclei and the electrons in atoms and molecules, while overall they are neutral. We have these charged particles that make them up. And so van der Waals forces act between all atoms, and generally the larger the molecule, the more electrons we have, the greater the van der Waals force. Dipole-dipole forces act between molecules with permanent dipoles. For that to happen, we have to have polar bonds, and we have to have these polar bonds and the dipoles reinforcing each other, not cancelling out. Remember that a polar bond was essentially made because we have a difference in electronegativity, an unequal sharing of electrons in our covalent bond. And hydrogen bonding acts between molecules that possess highly electronegative atoms, fluorine, oxygen, and nitrogen, and hydrogen atoms that are covalently bonded to it, so stuff like NH3, water, HF. And so generally we can then start to kind of draw out these tables here with our structures and various properties. So if we have a giant structure that is ionic, so an ionic giant structure, an ionic lattice, we know it has a high melting point because we're having to actually physically break the ionic bonds to separate these ions. And we know that it conducts in the liquid and aqueous solution states, but it doesn't conduct as a solid. If we have a giant macromolecular structure, we know that we have covalent bonding extending in this kind of infinite array, this three-dimensional covalent bonding. We have therefore high melting points because we have to actually break the covalent bonds between the atoms, which are strong. And we know that generally these don't conduct electricity, the only exception being graphite and something called graphene. Graphite we talked about as having our layers of these hexagonal carbon atoms, but we have delocalized electrons between the layers. Now graphene is just a one-layer thick version of graphite. So in graphite we have many layers of our hexagonal carbon atoms, those hexagonal layers because of the trigonal planar carbon atoms. In graphene we simply just have one layer, a single layer. But even so, even just in that single layer, we have trigonal planar shaped carbon atoms, so three covalent bonds, and a p orbital with a spare electron in it, so it's still able to conduct in the solid state. But diamond doesn't conduct electricity. If we have a simple molecular structure, we have covalent bonds, but we have low melting points because we are not breaking the covalent bonds when we melt or boil this. We are actually breaking the intermolecular forces, which are much weaker. And so generally we say that these don't conduct electricity. The only exception might be if they react to form ions in aqueous solutions, but that's not particularly common. And so generally simple molecular species don't conduct. And then finally we have a giant metallic structure. So we have metallic bonding, very high melting point because we have to actually physically break the strong electrostatic attraction between the positive metal ions that are in a regular lattice arrangement and our sea of delocalized electrons. And then because we have these delocalized electrons that are free to move and carry charge, it conducts in the solid and liquid state, and typically metals don't dissolve in water, but they may react. So, time to have a go at some questions. So we have some questions here to do with all the things we talked about in this video, and in particular the final question using the table on the right here to identify which type of structures things are and what type of bonding there is in there. So if you want to have a go at the questions, pause the video and the answers will be on the next slide. So the first question gave us the melting point for phosphorus, P4, of 317 Kelvin. Melting point for sulfur, S8, is 368 Kelvin, and to explain the difference in the melting points in terms of bonding. And so both the molecular phosphorus and molecular sulfur, P4 and S8, are both covalently bonded molecules. So we normally think of things like fluorine and chlorine, these halogens existing as diatomics, F2, Cl2. Actually, sulfur and phosphorus also exist as these covalently bonded molecules. So sulfur actually exists as what we call a crown structure, S8. 8 sulfur atoms all linked together. Phosphorus exists in kind of a sort of tetrahedral arrangement of these P4 molecules. Now, both of these are covalently bonded molecules, and so we have these strong covalent bonds that act between the atoms, but because they are simple molecular structures, they have much weaker intermolecular forces acting between the molecules. Now, because we have 100% covalent bonds here, we don't have any differences in electronegativity. Therefore, these are non-polar molecules, we don't have any dipoles, and so the only intermolecular force that acts, because we don't have an overall dipole, so we don't have dipole-dipole forces, we don't have any particularly massively electronegative atom or hydrogen attached, so we can't have hydrogen bonding, it has to be van der Waals forces that act. And we know that van der Waals forces increase with the numbers of electrons, essentially with the size of the species. And so therefore, because S8 is greater than P4 in terms of the molecular weight, but also in terms of the number of electrons it would have, there's therefore stronger van der Waals forces, a stronger intermolecular force, and therefore it requires more energy, a larger energy input to separate those molecules, and hence a higher melting point. Question 2 was to ask, how does graphite conduct differently to metals? Well, we know in a metal that we have this regular lattice arrangement of positive metal ions, and in between those we have our delocalized sea of electrons. So our metals, we have our delocalized sea of electrons. This conducts in all directions. It conducts in 3 dimensions, and it conducts as both a solid and a liquid. For graphite, remember, we have our hexagonal layers, our trigonal planar carbon atoms, with each carbon making 3 covalent bonds. And so therefore we have a spare electron in a p orbital. These p orbitals from the layers start to overlap. We end up with delocalized electrons. However, these delocalized electrons can only conduct along the hexagonal plane, not perpendicular to it, so not in 3 dimensions. And then finally, question 3 was to use the table, which I've reproduced here, to identify which structures are giant structures, metallic, macromolecular, ionic, covalent, and a gas at room temperature. So the first one, to look for giant structures. Essentially what we're looking for when we think about a giant structure is, does it have a very high melting and boiling point? Essentially the only one that doesn't have a high melting and boiling point is a simple molecular structure. Our giant structures, remember, are the ionic, the metallic, and the macromolecular. And these all have very high melting and boiling points because we're not breaking intermolecular forces in this case. We are actually breaking the bonding within the species. And so when we look at our table, we can see that A, C, and D all have very high melting and boiling points. And so they are our giant structures. Next one is the metallic. The key thing just to look at for metallic bonding is we know that metals conduct. The key thing is that they conduct when they are solid. If we look for the other thing we know that really conducts is our ionic compounds, but they do not conduct when they are solid, only when they are liquid or either sort of aqueous or molten. And so we have our top example here, substance A. We're told that it conducts when it's a liquid, but also when it's a solid. And therefore A must be the metallic structure. Macromolecular. Again, we're looking for high melting and boiling points here, but we know that generally in a macromolecular structure, we have covalent bonding. And so the key thing here is we need to see basically that there's no electrical conductivity when it is a liquid. If there is electrical conductivity and it's a liquid, then it's either metallic or ionic. So we need to look for the ones that don't have electrical conductivity as a liquid. That's B and D. So these must have covalent bonding within them. And then we have to just look at the melting and boiling points, because we know that if we want macromolecular, we need to have high melting and boiling points. B has a very low melting and boiling point, and therefore only D must be a macromolecular structure. To find out which is ionic, essentially we need to look for high melting and boiling points, as well as having electrical conductivity when it's liquid, but not when it's solid. Remember that we can't, ionic compounds can't conduct when solid, because their ions can't move, and we have to have the ions being able to move and carry the charge. And so if we look for high melting and boiling points, we have A, C, and D. And then when we look at our electrical conductivity, it's only C that conducts as a liquid and doesn't as a solid. A, which conducts as both a solid and a liquid, must be a metal. D doesn't conduct when solid or liquid, so must have covalent bonding. And so we're left with C, which can only conduct as a liquid, as being our ionic structure. Covalent structures, essentially we need to look either for a very low melting and boiling point, which we get with B. That must be a very simple molecular structure. Or we can have a macromolecular covalent structure, which will have a much higher melting and boiling point, but we have to look for no electrical conductivity as a liquid. And so therefore we end up with B and D for our covalent structures. And then finally, the one that will be a gas at room temperature. If it's a gas at room temperature, it must have very, very weak intermolecular forces. It must have a very low boiling point. That's going to be a simple molecular compound. And so we look for the very low melting and boiling points, and that's B. So B is a gas at room temperature. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.